I'm about to do the second problem for conditional probability, topic E, which is Leah's flying from Boston to Denver. So I will start this one by looking for individual probabilities. And that will be found in the second sentence that says the probability her first flight leaves on time is 0.15. When you start a tree diagram, you always have to make sure that you are starting with the individual probabilities. So Leah's flight can either be on time or it can be not on time. And if there's a 15% chance of it being on time, then there is a 215, an 85% chance, then it is not on time. Now, from there, if her flight is on time, we can move there. Her luggage will make it 95% of the time. And if her flight is not on time or is on time, it will not make it 0.05. So we subtract 1 minus 0.95 to get that. And that would be luggage not make it. Now, as we move on, we've got if her flight is not on time, the exact same choices about her luggage occur. Either it's make it or the luggage not make it. And if her flight's not on time, there's about a 65% chance her luggage is not going to make it home with her. But 1 minus 0.65 makes 0.35 that our luggage will not make it. Now again, a tree diagram is completely useless if you don't find the sample space by multiplying the branches. So as I multiply the branches, I'm going to get, for instance, 0.15 times 0.95, I'm going to get 0.1425. And then this will be 0.0075. This is 0.5525. And this is 0.2975. And I'll check those. They should add up to be 1. So again, what you just found, I'm going to highlight. This right here is the sample space. This is every possible outcome with these events that could happen. Okay, and again, just a reminder that these are ands. The ands are found at the end, so this is probability of on time and luggage make it. This is the probability of not on time and luggage not make it. This is the probability of not on time and the luggage makes it not on time and the luggage does not make it. And you're going to use that to answer your questions. Again, let me also point out that this right here, these first branches are individual probabilities. This is the probability that your flight is not on time. And we multiply that now right here on this branch right there. This is a conditional probability. So this is the probability that her luggage does not make it given that her flight is not on time. And when you multiply that, that's going to give you that 0.2975, which is the and when you multiply that. Okay, so what is the probability that her luggage is in Denver when she arrives? So for this one, all I'm going to do is I'm going to look at the sample space and find where her luggage is in Denver when she arrives. So if her luggage makes it, it's going to be in Denver with her. And if her Let's see if she's on time and her luggage makes it. And then right here is also, even though her flight's not on time, her luggage will make the connecting flight, so it will be there when she arrives. So I'm going to take 0.1425 plus 0.5525. And that is going to be 0.695. Okay. So here in letter B, we have a conditional probability. Let me change over colors here. Let's see, we'll go with the green one. It says, suppose you go to pick up Leah in Denver and her luggage is not there. What is the probability that Leah's first flight is delayed? So this is the given information. So again, this is important, the notation for these. You're looking for what is the probability that her flight is not on time under the condition that you know that her luggage is not there. So this is the luggage not make it. And again, this is flight is not on time. Given the luggage is not on time or luggage does not make it. Okay, so again, when you're doing your conditional probabilities, the bottom is going to be all of the places that the luggage does not make. So in green, you'll see this. Luggage is not making it, luggage is not making it. So those are the two that are going to go on the bottom. So 0.0075 plus 0.2975. Now, at the top of this, in the numerator, you have a choice. It's one of these two things. So out of these two star numbers that were at the end of my tree diagram, which one of these was her flight not on time? And that would come from the 0.2975. Which leaves us with 0.9754. Okay, last thing that we are going to look at is, are the first flight leaving on time and luggage making the connection independent events? So I'll go back to, if hopefully you remember that if I ever ask you if events are independent, we're going to start off by writing if independent. We're going to start off by assuming that they are. So probability that, and it says, are the flight leaving on time? So on time, given her luggage makes it, and I just want to see my notations. Luggage makes it. If they were independent, knowing her luggage made it would have no effect on whether or not her flight was on time. So that would equal the probability of on time. So it's our job to figure out if these two things are equal. Well, the probability of her flight being on time, we actually know, and they gave that to us at the beginning, that was just 0.15. Now you can find that in the sample space by looking up. So here's flight on time. Where's the other one on time? I missed that. This should have been on time. Let me change this. Maybe you saw that earlier. That's the on time. So if you add those two numbers, the 0.1425 and the 0.0075, you will also get the 0.15. So you can always use your sample space to do that as well. So if I go to find the probability on the left, which is her luggage does not make it, or her luggage does make it. So on the bottom, I'm going to go into the tree diagram and I'm looking for where does her luggage makes it. And that denominator is going to be 0.1425 plus, where else does her luggage make it? That would be 0.5525. And out of these two numbers, which of these are on time and luggage makes it? That would be the 0.1425. And if you figure out the math here, you will notice that these are not equal because 0.205 is not equal to 0.15. So we would say, therefore, they are not independent. And then I'm going to do the other side of this. You do not have to do both sides, but let's try. The other one would look like this. If independent, the probability that her luggage makes it given on time would not be impacted if they were independent, whether or not it was on time, so it would just equal luggage make it. And I'm going to put these numbers in and see if this makes sense to you. So if you add up everything in the highlighted yellow of where the luggage does make it, you will get 0.695. So I'm adding up everywhere 0.1425 plus 0.5525. Now, if you do that, let's see if it equals the left side, because this is the big question. So the denominator is going to be everywhere where our flight was on time. So that is 0.1425 plus 0.0075, which, by the way, does add up to be 0.15, which they gave you in the problem. And then what's the probability that on top, the luggage makes it and her flight is on time? So out of those two numbers, the 0.1425 would be chosen. And we can see that 0.95 is not equal to 0.695, which means, again, they are not independent. And you only have to show one side of the argument. You do not have to show both. Okay, thanks, guys. Hopefully this helps, and I will see you soon.